Hello and welcome to TidyX episode 48, the highly simulated episode. We're not really here. All right, so TidyX is a screencast where we go through and explain how our code works. My name is Ellis Hughes, and you can find me on Twitter at Ellis_Hughes.
And I'm Patrick Ward. You can find me on Twitter at OSPPatrick. And you can find the screencast on Twitter at tidy_explained. Or you can email us tidy.explained@gmail.com. Either way. Or you could comment on the YouTube.
Comment down
comment
below.
on the YouTube page.
We're seeing those. We like them. Like to hear from
Yeah.
y'all. Cool. All right. So this week, I think it'll be a fun one because we've kind of done a series now where we're combining a lot of techniques that we've used in past episodes. And this episode is no different. Patrick, you want to tell them what we're doing while I set up the our studio instance?
Yeah, we're going to do a Monte Carlo simulation. So the past few weeks we've done some hockey stuff, and I think it was last week we did last week. Yeah, last week we created team strengths, and then we used those team strengths to forecast the probability that one team wins over another.
Mm-hmm.
And we used an R optimizer to do that. Which is one way to do that. Another way would be to actually try and identify a known sample distribution, so mean and standard deviation for the teams, and then create a Monte Carlo simulation. So basically run a simulation where you're simulating an outcome of random variables based on this known mean and standard deviation. And we can use that to look at things like the probability that one team beats another, or we could use that to also flip it and ask the question, what's our forecasted point differential for this game? So if we were looking at like point spreads, and who would we give the edge to? So as always, we have to start by getting some data.
Yep, that's what we're going to do. So in our first couple lines here, we do what we always do, it seems, library and tidyverse to give us data manipulation abilities, as well as loading in data from a website as we do. So the next thing we have here is a function that we're going to be using to pull in the data for us. And so we're going to call this function pull NBA data because, we're very imaginative people here. And it's going to take an argument month. So the reason we have to do this is Basketball Reference this year looks like they've split out. So normally when we're looking at the data, when we're looking at a season's data, it lists it all in a single table there, and it's really nice. This season, it looks like they're doing a little bit different, where they're actually breaking it out by month. So if we were to go to basketballreference.com, leagues, NBA 2021 games, HTML, it actually only showed December for us. And so the way that this website is set up right now is you actually need to pass the month that you're interested in getting the data for. So currently they have it set up where it's got December, January, February, and March. Most of February and all of March right now don't really have values with a lot of NAs. So not a whole bunch of information we're going to be pulling from there, but let's step through this function first. So first we're going to create the URL. So paste together with paste 0, the month combined with the URL. So now we're going to get like basketballreference.com, NBA 2021 games -December.html. We wrapped to lower in month because it needs to be lowercase in order for the URL to work. And this way we could pass in a very strange uppercase, lowercase December, I don't know, capital D with a capital M if we're mistyping things, and it'll still work. It'll figure out what it wants to be doing. It'll then read in the HTML using read HTML. And then pretty much does our standard, what we do every time, it seems like, pull the page, pull out the HTML table. We set fill to be true, so it'll fill in any missing values. We're going to select that first table there, or explicitly select that first table there. There are no other tables on this data set, but it still returns a list. Convert it to a data frame and select. And in part of our select, we're going to be cleaning up some of the names. So like visitor, the original quote name is visitor.neutral. Then it has a points column, and we're going to call that visitor points because it is the visitor points. Home from home.neutral, h points from points.1, because it was repeating the points column in the HTML. And then we added this filter is not NA for v points because in the February table that we pulled, it didn't have all the data there, and we don't want to try to keep that and deal with that later on. We're like, let's just clean it right when we get it. So let's filter out any cases where visitor points is NA, because that would to me also mean that home points was also NA, and that just means that there's no data for that game at this point. So now we've created that function that'll pull in all the data for us. Now we're actually going to pull it using this chunk of code here. So we set the months that we are interested in pulling from. So this might be interesting in the future to be able to separate out, like we're going to train on December, January, and February, and then test it on March. I mean, that could be a fun thing to do. So we're going to pass our months. We're going to use the function from purrr map DFR. So it will execute our function for us. We're saying use pull NBA data. This tilde allows us to then specify if this function had multiple arguments where we wanted the months to show up in. In this case, we didn't really need to do it. It's just I like to do it for good practice. So we'll run that through, and so now it'll go through and from basketball reference pull in December, January, and February's data, and mapdfr will convert it into a nice data frame, pasting or R binding essentially all the data frames together. So we now have a single data frame with 328 rows. So there's been 328 games so far this year, and we have a data frame that is the visiting team, the points they scored, and the home team, and the points they scored. So let's take a head of that just to make sure. Yep, here we go. So Patrick, you want to take us through this code?
Yeah, so now what we need to do for the simulation to work is we have to get the team's points for and against, which we could have just scraped, if that's all we needed, we could have just scraped the aggregated season summary table and gotten their points for and against. But what's important here is that we also need the variability in points for. So we need to understand how variable a team is in scoring, because a team that has very little variability, we might have more confidence in night to night versus a team that's more variable, and they could be variable for a number of different reasons. So in order to get those values, points for standard deviation, and points against, we first create a vector of all of the team names, the unique team names. So was it 30 teams in the NBA? There you go. 30
yeah.
teams.
This was just to prevent us from having to write this all out and making sure that we only had teams that had played this season. If for some reason a team was like holding out for COVID reasons, I don't know.
Correct. Yeah. And then we're going to use a function here. So we're going to take all teams, which is the vector that we just created, and we're going to pass it into, again, map DFR, just like we did before, which is within that map DFR, we're feeding this function. So we're feeding a function that takes in those team names, and it takes in the NBA data, and it says, okay, for the home games, when is the home team, the actual team from that vector of 30 teams that we have, the all teams vector. And similarly, we do the same thing for the away games. And then we create this points for here, which is basically when find the mean of the NBA data of home points when it's the home game or home team's games, and the mean of, and same thing for the away team's games. So those are wrapped into or concatenated into a vector, so that the mean of all of those values, basically if it was like Detroit Pistons, it'll be a string of all of the times that they scored, whether they were home or away.
Mm-hmm. And this is the reason we have to separate it out is because there's two columns, and it's either going to be one or the other. And so we want to get the points. If they were home, we want to pull from the points column. If they're away, or the home points column. If they're away, we want to pull from the visitor points column.
Correct.
To get that team, the Pistons points for.
And this is a really elegant way of doing that. A very slow and non-elegant way would be to create a data frame and then create another data frame and bind the rows on top of each other and create now one column for each team, and it'd be a total mess. So we do the exact same thing for the standard deviation. And then we do the same thing for the points against. So we're looking for those teams and finding, on average, how many points did they give up in every game.
So critically here, we flip the which points we're recording for points for versus points against. Otherwise, they'd be the same values, right?
You get the exact same value. And then just handy dandy wrap it all into a data frame so that we have a nice kind of flat table that will explain the team, how many points on average they're scoring, how many points on average they're giving up, and then, how many points on average they're scoring, the variability in the points that they're scoring, and then on average, how many points they're giving up. And then as a little sanity check, we have the N number of games. This is important because, as Ellis said, the NBA or Basketball Reference changed the website to have the ticker for each month above the top. So when I originally ran this, we pulled it and we were like, wait, Golden State's only played 4 games so far. That can't be right. And that's how we identify.
We're like, wait, aren't they like 12 and something? Or...
Yeah, 12 and 10 or something like that.
So like, where is this? Where is this?
So there you go. So now they have 22 games and they're 12 and 10. So they're basically a 500 team. And you can see their point differential is basically even, right? Like they're giving up on average as many as they're scoring, with some margin of error, obviously, but pretty much an even team, right?
Yeah. There you go.
So now we have the data prepared.
Yeah. So now we have all the teams points for, standard deviation, the points they score each game, the average points that get scored against them, and the number of games they play. Now we've got this information. What are we doing with it?
Okay, so now we're ready to do a Monte Carlo simulation, and I'm going to step through just a simple way of doing this, and we'll make a little for loop and show you what it looks like. And then Ellis will do something more elegant and make it into a better looking function than what I had originally did. So for an example of how this is going to work, rather than working with the entire data frame, we'll just start with 2 teams. So let's pretend that tonight Golden State is playing the Los Angeles Lakers, and we want to get a sense for which team has the edge. Like, given the information that we know, who would we put the probability of winning on? And maybe like what kind of point differential would we expect if these 2 teams were to play? So we take team 1 and team 2. So the first thing we're going to need is the information from our flat table for each of those teams. So team 1 for Golden State, we're getting their points for, their points against, and their standard deviation of points for. And we do the same thing for the LA Lakers. Okay. So in order for the Monte Carlo simulation to work, remember, we're creating a simulation of a random draw from a known population of mean and standard deviation. And I will say that this works for normally distributed data. If we were in a sport like maybe soccer or hockey that's very low scoring and values, the games could end where a team has 0 points, things like that. This might not hold. We might have to use like a Poisson distribution or something that's like in counts. So that's just something to keep in mind. I don't know that. Maybe the point differentials look pretty good in hockey or soccer. I haven't looked at that, but it's just something to keep in mind. Like know the data so that when you're doing these kinds of simulations, you identify the correct distribution to draw from. Otherwise, you can get like wild estimates.
Yeah.
In order for our average, so the mean and standard deviation we're going to use, the standard deviation we know, which is the team's, the point differential or the points for standard deviation. For the team's scoring ability, we also need to account for their opponent's ability to give up points. And so we're going to create an average, an adjusted average of the team's points for based on the team that they're going against. So basically, we could do this with an arithmetic average. So we could add team 1's points for plus team 2's points against divided by 2. Or we can use what I used here, which is an average of sorts. It's using one of the other Pythagorean means. This is actually using the geometric mean. So it's the nth root. So n being the number of samples. So if we had like 3 or 4 teams within this, it's the nth root of the multiplicative of the two averages. And usually you'd see geometric mean in something like finance, where the percent increase in your bank account or in your investments is 10%, 20%, and 30% over 1, 2, and 3 years. It's compounding. And so you can't just take the mean of 10, 20, and 30. So because it's multiplicative, you would use the geometric mean. Here we're using the geometric mean as a way of being a little more conservative. Generally, the geometric mean is going to come out to be equal to the arithmetic mean, or actually slightly less than the arithmetic mean. So we're going to use that here to be a little more conservative in our mean and standard deviation. So there's our adjusted points. So right now we would expect, if those two teams played, we'd have an average points for Golden State of 109 and about 113 for the LA Lakers. And so let's just go ahead and simulate one single time. We're going to make a simulation of the game. So the way this works is we're actually doing a simulation within the simulation. So we're using QNorm, which is one of the handy dandy random number generator functions in R. And it's using the normal distribution, hence the norm. And the Q part means quantile. So it's basically feeding or taking, you could see the arguments there on the right, your usage, it says P. So it's going to take a probability value, so somewhere from 0 to 1. And it's going to say, given that probability value, 0 to 1, and the known mean and standard deviation, what value would we expect to be all the way on the left of that value in the distribution, right? And so within that, the probability that we're feeding it is run if, or R uniform, which is basically another random number generator, which is generating a random value from 0 to 1 out of a uniform distribution. Basically, uniform just meaning that any value from 0 to 1 has an equal probability of being selected. So when we do that for team 1, we feed this in and we run it, and we get a value of, okay, 114. We could run it again and we'll get a different value because it's simulated and we didn't set the seed. So now we get 96 and 136 and 100. And you can see why this is going to be valuable in a Monte Carlo simulation, because we're going to do this thousands upon thousands of times. And so we do the same thing for team 2, and we get the same type of thing, just specific to their mean and standard deviation. So those are the two kind of workhorses of this Monte Carlo simulation. And we're literally going to throw them into a for loop and let it plow through this 10,000 times. Mm-hmm. So we're going to set our n at 10,000. I used scientific notation because I was lazy and didn't want to put down zeros. So we set it to 10,000. And then we're going to set the outcome vector, which is basically a storage space. Mm-hmm. So every outcome that comes, we're just going to plop it into that vector as somewhere to house our outcomes from our for loop every time it runs through. I
need to generate n. And
generate
so
n.
You should always, if you're doing loops, preallocate. And this is preallocating. So this is basically telling R to tell your computer, hey, I'm going to be dropping in 10,000 things into this vector. Make the space for this now, so that it doesn't have to do that in the loop.
And can you explain? So I had when I originally wrote this code, I had outcome equals NA. And that's how I normally do it. And you said that's stupid, and you changed it. You changed it to that. Why did you change it to that?
So this is just generally good practice if you're going to be doing a for loop. People complain about for loops in R being slow. And they can be if you don't write your for loop in an efficient way. And it's very easy to write it in an inefficient way. Like the number of times I've seen people do an R bind within a for loop. And R binds are an incredibly expensive process for R to run, because the way that it works in the back end, it's very memory inefficient. So the best sort of thing to do when you're doing a for loop, but you want to be like building up information out of it, is pre-allocate memory, so that it doesn't have to do this as part of the loop that it's doing. So find a way to store it, but tell that storage in advance, hey, I'm going to be dropping stuff. I'm going to be dropping 10,000 things into this. Put that memory aside right now, so it doesn't have to do it later on. Because that is definitely part of why it takes longer to do it. So what we're saying is create a vector that is a character vector of length n, so of the 10,000 probabilities there.
Yep.
So R now has set aside this memory for us. So when it goes through and runs it and it drops in which team won, it doesn't have to go, hey computer, I'm running out of memory for this vector, please add more. It'll just, it already has that. Or it minimizes the probability that it's going to have to do that.
There you go.
That's really why you do that.
So now you know, and it's also not the first time and probably not the last time that I've been inefficient. Okay, so we're gonna run our for loop. We did a former TidyX, I can't recall the number, on basics of for loops. So maybe we can find that. They can be handy. So here we go. We're gonna run our for loop, and basically what I've specified here is for I in 1 to n. So basically for every value in the sequence of numbers 1 through that 10,000 or 1,000. Sorry, is it 1,000 times?
No,
sorry,
it's 10,000.
No, 10,000 times. Oh yeah, there's
it stops printing it.
Truncated it. Yeah. So every time through that 10,000 in the sequence of 1 to 10,000, we're going to run exactly what we ran above, our little Q norm simulations, and we're going to say, okay, team 1, Q norm for team 1 minus Q norm for team 2. Okay, that's going to give us our point differential, who won, and we're going to use if else to get a value of, okay, if the differential is greater than 0, obviously team 1 won. If it's less than 0, obviously team 2 won. That's the winner, and then we're going to deposit that into the character vector that we made. So let's go ahead and run our for loop. Boom. And now we have 10,000 vectors of winners and losers, and we can make a handy little table, and we can use prop table to get the percentage. So Lakers won about 59% in our simulation, and Golden State won about 41.4%, and we can make that into a cool little bar plot with base R if we want to look at it.
Ooh.
Yeah. Wow. Okay. So right now we have this feeling like, okay, we're giving the edge to the Lakers, and we could stop there. We could stop with the probabilities, but maybe we also want to play out and figure out the point differentials. And we've already calculated the point differentials in our for loop. So literally we could have created a vector of those differentials, and we would have been able to use that. And so why don't we do that in a more elegant way with a map DFR, and Ellis can take us through that.
Sure thing. So what we did really in the prior step that Patrick took us through was simulate a game, right? So this is a common thing when you're doing a simulation, is write a function that is like the single unit of thing that you're wanting to run as a simulation. And so in this case, we're simulating games. And so we're going to create a function to simulate a game for us. So it's going to do the exact same thing. It's going to have 4 different arguments: the team 1 mean and team 1 standard deviation, team 2 mean and team 2 standard deviation, that we're going to be using for calculating everything. We're going to simulate within that the scoring based off of the mean and standard deviation, using the same Q norm that we've been doing during this TidyX so far to get team 1 scores and team 2 scores. Then really that's all we're doing in this case. The only things that we wanted to manipulate as part of our simulation in this case here were the means and standard deviations of the scorings of the two teams that we're caring about. And so you can definitely get a lot more complicated, but we're keeping it very simple in this case here. So then we're going to have a data frame that outputs all the simulations, or the information about the simulation that we care about, which is what was the team 1 scoring, what was the team 2 scoring, what was the point differential, so how much more did team 2 score than point 1, or team 1, or no, how much more did team 1 score than team 2, excuse me.
Yeah.
Order of operations. And then also which team was called the winner. So did team 1 score more? If so, team 1 was the winner. Did team 2 score? If so, team 2 was the winner. And so that is the information that we're pulling out of our simulate game. So that now we have a function that we can just run at any point and go, all right, So I'm going to bet that team 1 mean is 100 and their standard deviation is 10. The other one is, 99 and their standard deviation is 5. There we go. So it took this random team and gave us all the information about their game. But we're still interested in seeing how Golden State and the Lakers played. And so we want to simulate their games. And so we're going to do the same. N is 10,000. We're going to do a seek len, which I prefer. We could do a 1 to n as well, and that is definitely, they're equivalent essentially. But I like seek len because it handles cases where n would be like 0 and whatnot. So this is just a general thing to do if you're trying to condition on a value that you're going to be passing to it. And we're going to throw it into map DFR. We're going to simulate the game. Team 1 adjusted mean, team 1 standard deviations and points 4, team 2 adjusted points, and team 2 standard deviation and points 4. And now we're going to simulate 10,000 games in 3, 2, 1, and it is almost done, and it is done. So, wow, they played really quickly. Like
10,000 games.
They're putting down some time. So,
and LeBron's not even tired.
He's like, come on, give me 10,000 more.
Exactly.
All right, so now we've got this data frame that has team 1 score, team 2 scored, the differential, and which team won. Mm-hmm. So now we've got, like, there's obviously a whole bunch of other things that you could include in this model, like we've said, but we're keeping it very simple. So we're going to take a head here. So team 1, team 2, point differential, and team winner. So all right, what did we want to get out of this? Well, we wanted to know, like, what's the point differential, right? Like what is the difference between the two teams on average? So we can do a histogram of this, and we can see that it's relatively normally distributed. Mm-hmm. There's some pretty big tails there that don't make a whole bunch of sense. Like, I don't think it's very common that a team loses by 50.
It's never gonna happen. Yeah, exactly.
or conversely wins by 50.
Right.
But that's it. That's why this is like simulated. It's fake. It's not, and it's just to like give us a distribution. But we're going to also add an AB line to this plot here. So this is going to be the mean point differential that's happening here. So as you can see, the edge is a little bit, it's negative. So we'd give the edge to the Lakers.
Yeah.
To win more. So this is kind of a nice way to visualize this. But what are the actual values? What are things that we actually want to care about? So we can do a quantile of the points differential. So this will give us the different quantiles that we might see here. So if you look at the interquartile range, which typically is like 25 to 75%, you could see that our simulation would expect anywhere from -15 to 8.
Right.
So that means we could expect anywhere from Lakers winning by almost 16 or about 16 points all the way to Golden State winning by 8 to 9 points.
Correct. So how confident would you be in is what what if you were like trying to pick it, how confident would you be that to select one team over the other, right?
I mean, based on this simulation, you're probably going to pick the Lakers, but of course we didn't take into account like
or you're going to pick Golden State to cover, to be within 4 points, right?
Yeah. So we'll quickly take the mean of the point differential, which is what on average is the difference. And here we're saying it's 3.68.
Mm-hmm.
So that's saying that on average, we're going to expect Golden State to lose by about 4 points.
And they've played once so far this year, and Golden State was able to win by 2 points. So it was a close game. They won by 2, so they covered. They covered the spread there.
Yeah. So here, if it was saying that they'd lose by 4, you'd probably say nah.
Yes.
And if you had on that game, you would have won something. But
right.
We're not promoting gambling.
Yeah. So and like what you'd want to do then is run this over all the games that have been played so far, and then get a sense for the margin of error within your estimates, and then that would help you to fine tune things and forecast games going forward. I mean, what we did here was a very crude Monte Carlo simulation because we're really not using all the available information. I mean, we literally just use points for and against, and it's kind of fun as a toy example. But what we might do is like figure out points for and against when a team is home or away, or maybe points for and against when a team has played two or three games on the road, and maybe fatigue is setting in and their ability to score or to prevent the other team from scoring is diminished. Or maybe points for and against if we know that a certain player is out and that's going to change the scoring differential. You know, if like LeBron is taking a day off, that might change drastically. All of a sudden there's, 45 points that he would normally score on a night. Those are going to have to be distributed over lesser, skilled players.
Mm-hmm.
So this is sort of a toy example. You could extend this out, and that's kind of the beauty of these types of simulations is, if you start really simple like this, you can always add and iterate the process with other information that might potentially add value to your estimates, and then you can test those estimates. And so that's kind of the fun part
historical
about it.
data. So
yeah, with historical data. Yeah.
There you go.
So that's Monte Carlo simulation.
Simulations using NBA data.
NBA.
There you go. So this is
nice.
fun. So thank you so much for joining us today and learning a little bit more about for loops, Monte Carlos, purrr, simulations, functions.
Scraping.
We covered a whole bunch of stuff again.
Yeah.
I think there we'll call it. Once again, my name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward, and you can find me on Twitter at OSP Patrick, and TidyX is on Twitter at tidy_explained, and we are also on Gmail at tidy.explained@gmail.com. And you can find us on our YouTube channel where you would be watching the screencast.
Subscribe. Please subscribe. We appreciate when you subscribe. Share it with your friends, family.
Share it. Thumbs it up.
Yes.
And if you feel inclined, comment on the in the comment section, and we'll try and get back to you.
All right. Thank you so much, everybody, and keep on exploring your world.